All right, guys, looks like the quiz is timed out. Just keep in mind every now and again, I do like to put one of those smart solution ones up there. That was, for example, the one with the atoms of zirconium. I won't do that every time, but every now and again, I like to put one of those in there because it's actually the closest Chem 101 allows me to actually have you show a setup on a problem. So be aware that you have to do a little more than just put the right answer in. You kind of have to show me how you got there. Now, granted, those sometimes take a little more time to do. So if you see one of those on there, my advice is probably save it to last because it's probably going to take the longest time to do and you want to maximize your points. So that's probably what I would do in a situation like that. Looks like most folks got to it, which was good. All right, so everybody see my white screen okay?
Yeah.
All right, perfect, thank you. All right, so let's get back onto empirical formula here, which is the topic of the video that we had for last night. And remember that the empirical formula is going to be actually the simplest mathematical reduction or representation of the molecular formula, which is the actual formula, okay? So for example, you had acetic acid on there. So I could write the formula that they gave you there. Turns out it was C2H3O2. And that's a molecular formula. So what you can do there is you could combine the H's here. So you could say that's really C2H4O2. And then you can see that you can divide everything through by 2. And this thing actually reduces down to CH2O. So that's how we go from a molecular formula to an empirical formula. I think almost everybody got that one. All right, so just a representation of what we were doing there. Now, I think I gave you guys a really simple problem in the video where everything kind of worked out really nice for you. And I also talked a little bit about where empirical formulas come from. So we talked about how we can actually do some sort of a chemical analysis where we actually have traps where we can catch products of the reaction, and we can weigh them and then reduce them down to the element in question and figure out by percent, by mass, how much of each one of those elements is present in your compound. Okay, so that's kind of nice because it shows you where the data actually comes from in an empirical formula problem. Now, normally in a textbook example like we see, you're just kind of given, for example, moles of stuff or grams of stuff or mass percents of stuff. And then from there, you have to work the empirical formula problem. But as long as you've got amounts of material, you're good to go in terms of the element, okay? Whether it's a percent, grams of the element, or moles of the element. You can always get to an empirical formula from any of those. So in most cases, like this example number 1, the material is going to be given to you in terms of percents by mass. And I think that's kind of how we talked about it in the video. So this will be the most familiar form in which you're going to be given information. So here's the deal. We got a compound that contains carbon, hydrogen, and oxygen only. And we did elemental analysis on it like we talked about in the video. And we found out that it was 74.01% carbon, 5.23% hydrogen, and 20.76% oxygen all by mass. Now, if you add all those up, they should come out to 100 or something really, really close to it. Okay, sometimes within experimental error, when you add them up, you might get like a little bit higher or a little lower than 100, but it should be really close to that. So we want to get an empirical formula out of this. Okay, so the way we actually start this problem is when you're given percents by mass, we're going to assume 100 grams of compound. And we do that because it makes the math easy. If I assume 100 grams of compound, percentages go directly to masses, right? So if I've got 100 grams total of compound, my 74.01% carbon just becomes 74.01 grams of carbon, right? So it keeps the math nice and simple. So that's what we're going to do. So anytime you see one of these percent by mass problems, that's the way to go about it. Assume 100 grams of compound, keep the math as simple as possible. Okay, so let's go ahead and write down what we've actually got in terms of masses. For carbon, we're 74.01%, or sorry, I'm just going to leave it as grams because we've already assumed 100 grams of compound. And what I want to do is convert that to moles. Once we got the masses, we take them to moles. Okay, so the mole is, again, always going to be our central unit here. And that's going to be carbon. I should have put that up there. So I know that for every 1 mole of carbon, periodic table tells me I'm going to have 12.01 grams. I have 1 grams of carbon. Straight out of the periodic table there, guys. And keeping track of all my sig figs, I'll get 6.162. And that's going to be moles of carbon. Okay. Now we can do the same thing for the other elements. All right, if we have 5.23% hydrogen by mass, well, that's going to be 5.23 grams of hydrogen in our 100 gram sample. And I've got 1 mole of hydrogen, and the periodic table tells me that's what, 1.008 grams of hydrogen. Okay, and we can do the math there, and we get 5.19 to sig figs. And that's hydrogen. And then finally, we can do the oxygen, very same way. So if I'm 20.76% by mass oxygen, and I got 100 grams of sample, I got 20.76 grams of oxygen. That should be hydrogen up there, by the way. Keep track of my identities here, just like I tell you guys to do. So for every 1 mole of oxygen, I've got 15.9998 grams of oxygen, again, from my periodic table. And to sig figs, that turns out to be 1.298 moles of oxygen. All right, so the next thing we do in any problem like this is we actually have to now figure out the formula based on the moles. Now, the way we're going to do this is we're going to ratio things. So I think I set one up in the video like this. So what I'm going to do is I'm going to write my carbons. So every element I've got, I'm just going to write it out. I've got hydrogens and I got oxygens. And now what I'm going to do is I'm going to write the number of moles as sort of a subscript after each one, the number of moles that I've got. So carbon, that's 6.162 moles of it. Hydrogen's 5.19 moles, and oxygen's 1.298. The next thing we do is we're going to divide all of these through by the smallest amount. So I look through and I say, okay, which one has the smallest number of moles in there? It's not carbon, it's not hydrogen, it looks like it's oxygen, right? So I'm going to ratio everything by that number, the thing that's the number of smallest moles. And I think we did this in the example in the video. And in that example, everything came up all hunky-dory, right? We got nice whole number ratios out of those things. Now, the reason I picked this example is because sometimes that doesn't happen, okay? So if you actually work this out, here's what you get. You get C 4.75. You get H4. And you get O1. Okay, so hopefully everybody got the same ratios as I did there. Okay, so you look at that and say, but wait a minute, in any empirical formula problem, I know those ratios have to come out to whole numbers, but I got a fractional ratio there. So in other words, another way of writing this is I could write this as C4, and then what's 0.75? That's the same thing as 3/4, right? So I could write that as 4 3/4 hydrogens, or sorry, oxygens. Hydrogens 4, oxygens 1. So now everybody knows that I could take that 4 3/4 and I could turn that into a total fractional quantity. So we know how to do that. We say 4 times 4 is 16, 17, 18, 19. We add the 3. So I could rewrite that as C 19/4, right? Everybody remember how to do that from what, 7th grade or whenever you do fractions like that? H4, O1. Now, the reason I wrote it that way is because I need to come up with a multiplier that I'm going to multiply this whole empirical formula through by to get rid of that fractional 4. I want to get rid of that 4 in the denominator. So if I want to get rid of the 4 in the denominator, I got to take this whole thing and multiply it through by what? How do I get rid of the 4 in the denominator? I got to multiply everything through by
4.
4. Yeah, you got it. Bingo. Okay. So when I do that, I'm going to get C. Oh, Siri thinks I'm talking to her. I don't know why Siri thinks I'm talking to her. I didn't tell her that I was talking to her. I tell you what, she's like my wife. All right, so I get C19. Let's see, I got H16 and O4. Okay, so everybody see how I did that? And that comes up from time to time. It's actually not at all unusual to run into a situation where you have some sort of a fractional amount left over when you work those initial ratios out. And you got to basically undo that fraction. You got to get rid of it. Get everything in terms of whole number quantities. Okay? Sometimes you'll see it, sometimes you won't. Everybody good with that?
Wait, so you, for that one with the fraction, you multiplied it by 4, and that's how you get, okay, that's how you get 4 by 19, okay.
See what I did that? I mean, you could do the same thing from 4 3/4. You look at that and say, okay, well, how do I get rid of a 3/4? Well, I have to multiply through by 4 to get rid of the 3/4 and turn it back into a whole number. I mean, that's another way you could think of it. I like to do it in terms of just getting everything in terms of one of these all fractional numbers instead of a whole number plus a fraction. Just makes it easier for me to see that way. So again, that's one of those things that's going to pop up from time to time that you're going to need to worry about. It's not much to worry about. And another thing I'll just mention while I'm there is that when you see those kinds of fractional amounts left over, kind of look for basic normal fractions, right? So if you see a 0.75, okay, you know that's 3/4, right? If you see a 0.5, oh, that's a half, right? If you see a 0.25, oh, what's that? That's a quarter. If you see a 0.66, right? That's like 2/3. So keep in mind, you need to kind of think in your mind how to convert from a decimal quantity to a basic fractional quantity. Okay, so again, that's something you may have to practice with if that's not something you've done in a while, because you'll see things like that. And sometimes you have to round up or down a little to get to some sort of a fractional amount that sort of makes sense, if you know what I mean. But it's generally going to be something like that: a half, a quarter, 3/4, 2/3, a third, something like that. All right, so let's look at example number 2 here. So we got a compound here that's going to be 99.34% carbon, again by mass, and 5.66% hydrogen, again by mass. And this one, through an independent measurement, has a molar mass of the actual compound of 178 grams per mole. Okay, now this is an important piece of information because it allows us to take the question one step further. Because notice what I'm asking for here. I'm asking for us to get the empirical formula, which we can get through the percents by mass, but I also want the molecular formula. Okay, so here's the deal. If I want to get to a molecular formula, I need 2 pieces of information about the compound. I need the empirical formula, and I also need the molar mass of the compound. As we're going to find out, if I have those 2 pieces of information, I can get to the actual or molecular formula of the compound. Okay, so we're going to see how to do that. Okay, so let's start with the empirical formula because, we already know how to do that. So again, I got percents by mass here. That should be a 94. Sorry, I don't know why I wrote a 99. That doesn't add up. That should be a 94.34. I'm looking back at my notes and that's what it should be. Otherwise, you go way over 100%. Look at that going, nah, that can't be right. Okay, so let's look at carbon first. So if I've got percents by mass of carbon and hydrogen, I'm going to assume I got 100 grams of compound, right? So I can take those percents right to grams. So for my carbon now, looks like I've got 94, not 99, but 94.34 grams of carbon. Let's go ahead and take it right to moles. Okay, so I know that 1 mole of carbon has a mass of 12.011 grams of carbon, and that's going to take me to 7.854. And there's my moles of carbon. Okay, let's do the hydrogen. So So I got 5.66 grams of hydrogen. And I know that every 1 mole of hydrogen is 1.008 grams of hydrogen. Okay. And let's see what we have here. That's going to turn out to be to sig figs 5.62 moles of hydrogen. All right, so now since we're only dealing with carbon and hydrogen, right? I'm going to put my carbon here and I'm going to put my hydrogen here. And now we're going to put the mole amounts as a subscript under each one of them. So I got 7.854 under the carbon. That's my moles. Hydrogen's 5.62 moles. Oh, which one am I going to divide by? Which one is going to be the one that goes in the denominator for both?
Hydrogen.
Yeah, the hydrogen, because it's the fewer moles, right? You always pick the one with the fewest number of moles. Good. Okay, good. So when I do that, here's what I get. I get C 1.40 H1. All right, so what's the 0.40? What does that look like? Well, that looks like 4 over 10, right? So what does 4 over 10 reduce to? That reduces to 2/5, doesn't it? Okay, so I could rewrite that as C 2/5. Well, it should be 1 2/5 H1. Okay, and now if I want to, I can say 1 times 5 is 5 plus 2 is 7. So that could be C 7/5, right? Another way of writing that, H1. Okay, so now if I want to get rid of that fraction, right, what do I have to multiply everything through by?
5.
5, you got it. Remember, because the 5 will cancel with 5 if I do that. So that's going to give me a C7H5. Okay. So that's actually going to be my empirical formula. So I'll put EF by that for empirical formula. So that's the simplest mathematical reduction of the actual or molecular formula that I have. So that's part 1. Now part 2 says, how do I get from the empirical formula to the actual or molecular formula? Okay, and here's how I do it. I'm going to do it by a comparison of molar masses. Okay, so I know the molar mass of the actual compound, the molecular formula of it. It's 178 grams per mole. So what I want to do is I want to calculate a molar mass for the empirical formula. Okay, and we all know how to do that. I don't think I have to show the calculation, but if I do a molar mass for the empirical formula, I'm going to end up with 89.12 grams per mole. That's the molar mass of the empirical formula. So if I want to get back to the actual formula, what I'm going to do is I'm going to ratio the actual molar mass of the compound to the molar mass of the empirical formula's molar mass. So here's what I've got. What I say it was 178 grams per mole. And that's going to be for the actual. And I'm going to divide that by the molar mass for the empirical formula, which is 89.12. So I'll put EMP for empirical, so you know what it is. And what I'm going to get there to the nearest whole number is going to be 2. So what that's telling me here is that I need 2 of the empirical formulas to get to the actual molecular formula. So what that means now is that I could think of this in terms of a molecular formula as C7H5, that's my empirical formula, taken twice. So now, if I go ahead and do that, that's going to give me what? C14, if I multiply through H10. Okay, so that's going to be my molecular formula, or my actual formula. And that makes sense if you think about it, because if you reduce it down, okay, you're going to end up with the empirical formula back again. And the best way to reduce it down, or the only way really to do it, is to divide everything through by 2. And that gives you the C7H5 back again. Okay, so you see how I can use the molar mass of the compound, which again I can get from an independent measurement, plus the empirical formula to get back to an actual molecular formula. And that's another iteration of this that you might need to know how to do. Any questions about that, guys? And again, I'm trying to kind of sort of show you all the tricks that you're going to need to know as you go through this and you run into these kinds of problems. They're not hard, they just take a little practice. But just like anything else we do in chemistry, basically, there is a procedure we go through. Okay, so it's just practicing until you're comfortable with that procedure. If you can do it for one, you can do it for any of them. So that's the nice thing about what we do here. It just takes a little bit of practice to be familiar with it. Now, where we're going to go next in the next video is into combustion analysis, which is kind of taking empirical formula to a new level. Because in that case, what we're going to do is we're going to get back into that whole business of elemental analysis. And what we actually do there is, if we want to have, for example, an empirical formula of, say, a hydrocarbon, something that contains carbon and hydrogen, we can burn it. Okay, and I think we talked about that when we did elemental analysis, but basically we burn the stuff. Okay, and when we burn it, we make products. That's how we get to the products that we can trap and weigh. So this kind of brings us to the next level of this, where we can actually take the masses of the actual compounds that we trap, which in many cases might be things like carbon dioxide and water, and we can go from masses of those back all the way to an empirical formula. So it's adding sort of another layer to our empirical formula determination here, working from more original data, if you will. So that's what the topic of the next video is going to be. Okay. And we'll talk about that also on Friday. We'll go through some more examples of that. So let me pop back over into Chem 101 here, guys. And let's look at a few in-class exercises here. All right, I want to just look at this before I give it to you because I want to see if I think I'm going to remove one of those. So I'm probably never going to give you a problem like that. Okay, good enough. Let's go ahead and start it. Okay, you got about 15 minutes, which is probably going to be more than you're going to need. And that should work out just about right. Ah, yes, number one's a good example of what we just did. Number two is kind of interesting because notice that most of you have gotten it, that you can't really reduce it any more than it already is. So in this case, what you've got is a situation where the molecular formula is actually the same as the empirical formula. And that can be true. Okay, think about water, for example, H2O. Is there any way to reduce that down any further? No, there isn't. So in that case, the empirical formula is the same as the molecular formula. And this is one of those situations as well. Any questions popping up so far for you guys, or it looks like you guys are doing fine?
Can I have help on number 3?
Yeah, of course. So it says to write the empirical formula corresponding to, heck, we'll just write it here. I think we're still sharing here. C6H4Cl2, that one. All right, can we reduce that at all? Is there anything we could divide everything through by to get it to reduce? Looks to me like the best we could do is 2, right? So that ought to reduce to C3H2Cl. And I'll just put a 1 there just to emphasize that. In many cases, you just leave the 1 off. Does that make sense?
Yeah, sure. Thank you, Professor. I kind of forgot how to do it. So,
Hey, no
thank you.
problem. Not a problem. Looks like most of you guys are getting a little twist in 4 and 5. That's one where basically, if you look at 4, you got 2 elements, iron and oxygen, but they only give you 1% by mass, and they give it for the oxygen. So how do we get to the iron percent by mass? How would you do that?
Wouldn't you just subtract the oxygen mass from 100?
Yep, that's exactly what you do, because the iron's the only other thing present, so that has to be the difference between 100 and 22.27. Yep, that's exactly right. So that's another little twist that sometimes shows up in these empirical formula problems. That also shows up in 5. Now they gave you 2. They give you oxygen and carbon, but they don't give you hydrogen, but you can get hydrogen by difference. Yeah, and most of you guys are getting that, so that's good. Looks like most of you guys are done. You got about a minute left, so if you're still working, feel free to continue to work. just a few reminders. We're coming up on Friday, right? So you guys have a Friday quiz coming up. So remember to look back over what we've done since last Friday, because that's going to be the bulk of the material that's going to be on that quiz. And let me remind you guys again also about the utility of the homework. I was on the homework kind of checking you guys' progress here a few days ago, and just noticed a lot of you guys are not making much progress with the homework. Yeah, granted, the due dates are way out, so it's not an issue with points, but remember, the homework is a really great vehicle to help you practice. And I think for some of us, the material is becoming a little bit less familiar as we start getting into these mole calculations and things like this. So it's a really good opportunity to get in there and make sure you're practicing with the material. So when you see it on the quiz, you'll be able to go at it in a good, organized fashion and get those answers. So don't forget to do that. Again, I'm not, putting any pressure on you, but it's a really good tool to use to kind of help you out. Because again, the stuff that's in the homework looks a lot like what I'm going to ask you to do. So make sure you're practicing, guys. That's the big one. Any other questions? All right. That's pretty much all I got for you guys today. So please enjoy the rest of your day. It's really pretty outside today, so get outside and do something if you can. And I will see you.